I have a problem that I want to show you. It's determining the equilibrium constant K given some concentrations at equilibrium. So now that you know how to draw a mass action expression, that would be the first part. So it's going to be the concentration of the product, happens to be CH4OH, divided by the concentration of the carbon dioxide times the concentration of hydrogen raised to a power of 2. That 2 is because of the 2 coefficient there. So now all I'm going to do is plug values into that. So according to the problem, the amount of that has to be CH. Yeah, it's not CH4, it's CH3. Not a big deal. Get rid of that. Get rid of that. Because there's no such thing. So this needs to be CH3. And that was CH4. No, did it again. CH3OH. Yeah, whatever. Anyway, I'm going to put numbers in for this. So it will be 0.002 divided by, now the CO2 concentration was 0.2. 0.2 times the H2 concentration, which is 0.15. And now I'm going to have to square that. A little squared there. The square coming from this coefficient 2 goes to square that amount. And I get my calculator, and I'm going 0.002 divided by 0.2 divided by 0.15 and then 0.15 again. And I end up with an equilibrium constant worth 0.44. One of the things you see, it's less than 1. So you would say, because of that, because that's less than 1, you'd say the reactants are favored, and sure as heck the reactants were in a greater quantity than the products. All right? So another little more difficult problem, but not really, might look like this. Let's say I sort of have this hypothetical equilibrium, 2x going to A plus 3C. Okay? And the problem says, all right, K is going to be equal to 6.2 times 10 to the minus 3. And it also says at equilibrium, so this would be a problem, the concentration of A is equal to 0.03 molar, and the concentration of C is going to be equal to 0.15 molar. Find, that's what I'm looking for, find the concentration of X at equilibrium. Alright? So, it's really not that tough. I'm going to do the same thing again. I'm going to sit there and set up a mass action expression stating that it's going to be the concentration of A times the concentration of C cubed, the cubed again coming from that coefficient 3, divided by the concentration of X squared. Alright? So I'm just going to plug some numbers in there. That will equal, concentration of A was 0.03 times the concentration of C, which is 0.15, and I'm going to have to cube that because of that 3 coefficient there, divided by X squared, all being equal to 6.2 times 10 to the minus 3rd. Alright, so the math is a little trickier on this. So what I'm going to end up with is 0.03 times 0.15 times 0.15 times 0.15. I'm going to end up with 1.01 times 10 to the negative 4. Okay, so what I did is I just multiplied, that's this amount right there. That then is going to equal So I'm moving the x over to that side. 6.2 times 10 to the minus 3x squared, x squared. So now I'm going to divide, and I'm kind of losing, I'm just going to go half page. Okay, so now I'm going to have 1.01 times 10 to the negative fourth divided by 6.2 times 10 to the negative third equaling x squared. Now for a little magic of mathematics, x is going to equal the square root of 1.01 times 10 to the negative fourth divided by 6.2 times 10 to the negative third. Alright, so I'm moving pretty fast, but anyway, so I'm going to go 1.01 times 10 to the negative fourth divided by 6.2 to the negative third, and I get the square root of 0.016 equaling x, and then take the square root of that. So x is, the concentration of x is going to be 0.13 molar. So anyway, try that. The math was, but that's a way. Utilizing K, okay, I had that, 6.2, well actually not with that, but 6.2 times 10 to the negative third allowed me then to determine what the concentration of one of the reactants was, or what the reactant was.